Dear students, today I am going to discuss measurement of synchronous impedance of a three-phase alternator. For this, we need to perform open circuit test on three-phase alternator and short circuit test, and with the help of these two readings, we will evaluate synchronous impedance of the three-phase alternator. So first we will discuss open circuit test, then we will discuss short circuit test, and then we will discuss the procedure for evaluating synchronous impedance, followed by some numericals which are generally asked in various exams, particularly in GATE exam. So under this test, for open circuit test, we keep the terminals of the alternator open circuited, that is, no load is connected. Now the rotor driven by some prime mover is rotated at synchronous speed. So point number one, keep the stator terminals open circuited. Point number two, run the field winding, that is rotor, at synchronous speed by means of a prime mover. Now for a particular value of field current, we know that EMF will be induced in the three phases of a stator winding of this alternator. As load is not connected, that is, terminals are open circuited, so there will be no any drop, that is, the currents in the three phases will be zero, and hence no drop will be there. So whatever EMF is induced, let us say EPH, let us say this is EPH, so as there will be no any drop, so this will be same as VPH, that is terminal voltage, per phase terminal voltage. This is voltage drop between this point and neutral point. So terminal voltage becomes equal to EMF generated, as no drop will be there, no armature reaction, as current is not there. Fine. Now we will vary the field current, and for various values of field current, this VPH will be measured and plotted. So if we are going to take EPH, that will be equal to VPH here on vertical axis, this is 0, and field current here on horizontal axis, then we will get some plot like this. So if we will extend this linear part, so we will get one line. So what can we observe? For a smaller values of field current, the variation in EPH or VPH is linear, directly proportional to this field current. It varies linearly. But as IF is higher, if IS increases further, then the rate of increase decreases and rate becomes 0, that it gets saturated. It means further increase in field current will not result in further increase in terminal voltage or induced EMF. So this part is known as unsaturated region, linear region, and this part is known as saturated region. So this extended line is known as air gap line, AGL in short, air gap line is represented by AGL, air gap line. This is saturated part. Why it happens? Why we do not get linear region for all the values of IF? Why we are getting linear region for a smaller value of IF, not for higher value of IF? This is because as IF increases, what is IF? IF is field current, excitation current provided to the field winding. As IF increases, the iron parts of the machine get saturated. We know it very well, and because of nature, we get saturation in this curve also. Fine. So this was all about open circuit test. Now the second test needed for measurement of synchronous impedance is short circuit test. So we discussed open circuit test, and this is performed at no loads, hence this is also known as no load test. So the corresponding characteristic will be known as open circuit characteristic, represented by OCC. Open circuit characteristic. This is characteristic between VOC, open circuit terminal voltage, and IF. Fine. Now we will discuss short circuit characteristic. For that, we will short circuit these terminals. So the three terminals are short circuited as shown in the figure. So under short circuit test, first step is short circuit the three terminals as shown. Again, step number 2, run the rotor at synchronous speed by means of a prime mover. Now, as we have shorted the terminals, so even a small EMF induced in the armature will cause significant current to flow, and the corresponding readings can be read with the help of ammeter. Fine. So rotor is running at synchronous speed and field current is varied from 0 to some higher value in a small state. Care should be taken that the field current should not exceed a particular value, which gives rated armature current, that is the reading of this ammeter once shows ISC equal to rated armature current, then we should stop increasing field current. So under this short circuit test, we will obtain one characteristic known as short circuit characteristic, that will be between this short circuit current and field current. As we discussed, by varying field current, this current will vary. So the plot will be like this. This will be linear, a straight line. This is basically a straight line. Something like this, and known as short circuit characteristic. So this will be linear. Nowhere it will not get saturated. Why? Because under short circuit test, the range of field current is so small that it will not cause saturation of iron parts of the machine. So if iron parts of the machine are not saturated, so the relationship between this output and input signals, field current and short circuit current, will be linear. That is, short circuit current will vary linearly with the help with the varying IF. Fine. So once these two tests have been performed, then we can evaluate synchronous impedance like ZS is equal to open circuit voltage upon short circuit current. At same value of field current. IF should be equal to same. What does it mean? So earlier we have open circuit characteristic, something like this, some linear part then get saturated. Fine. This is OCC and this is short circuit. So if we will take, let us take this as rated terminal voltage, V rated. So at same value of field current at which we are getting rated open circuit voltage, the current, let us take this axis here. Okay, let us take it here, somewhere here. This axis is for ISC. Instead of taking this side, this is ISC and this is VOC, open circuit voltage, or EPH equal to VPH, whatever it is, right? So at the same value of field current, which gives V rated in open circuit test, will give this, let us say ISC1. So we will get ZS equal to this V rated upon short circuit ISC1 current for same value of IF. So not only at this value of IF, at any value of IF, so let us say this is another IF1. So at this we are getting this as open circuit voltage and this as short circuit current. So ratio of this upon this will give ZS, value of synchronous impedance at this particular value of IF. Again, at any other value of IF, because condition is IF must be same, at the same value of IF we have to take the two readings of open circuit voltage and another one is short circuit current, and the ratio will give you ZS. So ZS will not be constant for any value of IF, it will vary for different value of IF. So if we want to plot IF, so IF may be plotted and it will be something like, let us say this, and it will vary. Once it gets saturated, so with increasing value of this ISC, it will decrease, continue to decrease. So we are not getting constant value of ZS. This is ZS basically, plot of ZS. So we can observe that for higher value of ZS, higher value of IF, ZS is lesser, while for lower value of IF, ZS is higher. So the value of ZS in unsaturated region is higher than the value of ZS in saturated region, as can be observed. Fine. Let us plot the same here. So we have two axes. One is VOC or VPH, EPH whatever EPH is VPH. In open circuit test, this is 0, this is IF, and we have another axis of ISC. Fine. So we have two characteristics. Open circuit characteristic, and we have another characteristic, short circuit characteristic. So as discussed earlier, that synchronous impedance will vary with varying field current. So for the purpose of performance analysis of the synchronous machine, we need to take the value of ZS corresponding to the field current which gives rated terminal voltage. Fine. Otherwise, for other values of field current, we will get ZS, but that will be different than this one. So let us mark rated terminal voltage V rated. Let us write it V rated. Read it V rated. And let us say this is a point where we are getting V rated. Okay, let us mark it V rated. So this is field current. Let us represent IF1. So at IF1 field current, we are getting the open circuit voltage equal to V rated, rated value of terminal voltage. Fine. Let us take the point corresponding to IA rated. Let us mark this point. This is the short circuit current corresponding to rated armature current. Under short circuit test, we will get one point which gives the field current corresponding to rated armature current. If field current is lesser than this, then we will get armature current, current in the armature winding lesser than rated. If we will further increase field current, then we will get higher on this. Fine. Let us extend it further for more clarity. This is short circuit test characteristic in short circuit test. So let us mark this current also, ISC1. Okay, mark it ISC1. So this is the point corresponding to the field current which gives rated terminal voltage in open circuit characteristic, and this is the point which gives rated armature current in short circuit test. So the short circuit current, because this varies linearly, so we can extend wherever we want. No need to have further test, because once we know that this curve is linear, so we can extend it wherever we want. So after extending this curve, we will get one point corresponding to this IF1, and let us say this. Now observe carefully how questions are being asked in exams. In exams, out of these two field currents, IF1, IF2, and IA rated and ISC1, any three may be given directly or indirectly, and fourth one you have to evaluate. How? We have one triangle, this right angle triangle, and we have another right angle triangle, this. So obviously these two right angle triangles are similar always. So if we will take, let us say this is some angle theta. So if we will take tan theta in this larger triangle, so we may write ISC1 tan theta, that is perpendicular upon base, upon IF1. See, in this right angle triangle, tan theta will give this ISC1 upon IF1, and in a smaller this triangle, right angle triangle, tan theta, the same tan theta will give this upon this, and this is IA rated upon IF2. So just try to understand this relation. I think any problem can be solved based on open circuit test and short circuit test. We will see now after this. Fine. The ratio of these two field currents, IF1 and IF2, is known as short circuit ratio. What is this? Short circuit ratio. What is this? This is basically ratio of two field currents, IF1 and IF2. You know what is IF1? IF1 is the field current which gives rated terminal voltage in open circuit test. And what is IF2? IF2 is the field current which gives rated armature current in short circuit test. So how we will define short circuit ratio? Short circuit ratio is ratio of field current which gives rated terminal voltage in open circuit test to the field current which gives rated armature current in short circuit test. That's it. So in problem, if short circuit ratio has been asked, so easily you will get IF1 upon IF2, nothing but ISC1. Okay, if you want to write short circuit ratio, this, so this will be from here, you will write IF1 upon IF2, and this will be nothing but IF1 upon IF2 will be ISC1 upon IA rated. This may further be written as ISC1 upon IA rated. Fine. You know each and every term being used in this relation as already discussed. Fine. Now quickly we will solve 1-2 problem, sample problems asked in GATE exams to understand this concept better. Fine. Which can be applied in the problems asked anywhere. Fine. One more thing, once ZS is evaluated, this synchronous impedance, then we can evaluate XS, that is synchronous reactance, and that will be nothing but ZS square minus RA square, where RA is armature resistance. As we know that ZS is nothing but RA plus JXS. Fine. So this implies ZS square will be equal to RA square plus XS square, and then from here we may write XS square is equal to ZS square minus RA square, and hence XS is equal to ZS square minus RA square. If the value of RA is given in the problem, use it. Otherwise, if not mentioned, then it means RA has been ignored. Generally RA is ignored. If not mentioned and not given, it means by default it will be ignored. So whether we will talk about synchronous impedance or synchronous reactance, if RA is ignored, then both will be the same. If given, then we will use this formula to evaluate XS. Fine.